Hi there, let's continue with the next section, 6.2, line integrals. Your homework is problems 55, 67, 69, 78, and 83. So to begin, suppose you want to integrate over any curve in a plane, not just over a line segment on an x-axis. Such task requires a new kind of integral called a line integral. Scalar line integrals. A line integral gives us the availability to integrate multivariable functions and vector fields over arbitrary curves in a plane or space. There are two types of line integrals, scalar line integrals and vector line integrals. Scalar line integrals are integrals of scalar function over a curve on a planar space. Vector line integrals are integrals of a vector field over a curve in a plane or in space. Now, just as before, I kind of skip over this idea of the application of the Riemann sums, but here think of these as section pieces of arc lengths. And the idea is that to find this integral, we can go ahead and break up these line integrals into segments, and thus the sums of these broken up pieces would give us the integral that we are going to use. So let's go ahead and jump into integration. Theorem 6.3, evaluating a scalar line integral. Let f be continuous with a domain that includes a smooth curve C with parameterization of Rt, where T is bounded between A and B. Then the integral from B to A of f of Rt times the magnitude of R prime t dt. So we're going to, let me just spell it out in words. We're going to go ahead and start off by changing the variables. So that we are in T. And you'll be given some type of information about that. And then that would come from your R of T. And then we're going to take your R of T and find the derivative. And once you find the derivative, you want to go ahead and find that derivative squared and added and square rooted, right? As you have here in theorem 6.4, scalar line integral calculation. So we gotta find that magnitude. So we take each term from our R prime of t, square it, and take the square root. Okay, let's go ahead and do an example. Find the value of the integral c of x squared plus y squared plus z ds, where c is a part of the helix parameterized by R of t equals cosine t, comma sine t, comma t, where t is bounded between 0 and 2 pi. So according to our definition, we're going to find the integral from some bounds b and a, which in our case would be 2 pi to 0, of f of r t, and then we want to go ahead and find the magnitude of r prime of t, so that we are in terms of t. All right, let's go ahead and do that first part. Let's find f of r of t. All right, so my function f is x squared plus y squared plus z. Now we're given that x is cosine t, y is sine t, and z is t. So let's make those changes so that I have cosine t squared plus sine t squared plus z, and z is just t. And you should be able to notice that cosine squared plus sine squared, using Pythagorean identities, that gets us back to 1. So I have 1 plus t for our first part right here. Now let's go ahead and find r prime of t. So we're given some value r. In our case, it's cosine t sine t. and t. Let's go ahead and take the derivative of each one. The derivative of cosine is negative sine. So I have negative sine t. The derivative of sine is cosine t. The derivative the derivative of t is 1. Okay, let's go ahead and find that magnitude so that we have negative sine squared sine t squared plus cosine t squared plus 1 squared all under a square root, which gives us sine squared plus cosine squared plus 1. Well, we know sine squared plus cosine gives us 1, so I have 1 plus 1, so I have square root of 2. We just found this part here. Now we can go ahead and continue with our integral. So what do we have? We're trying to integrate from 2 pi to 0, and our value is, first we have that f of rt, which is 1 plus t, times square root of 2 dt. And there we have it. I'll let you go ahead and do the integration. Your answer should be 2 square root of 2 pi plus 2 square root of 2 pi squared. And that gives us 2 square root of 2. If we factor out that, we're left with pi plus pi squared. All right. Now, keep in mind this integration because we're going to do it again in the next example, but with a different parameterization. So next example, find the value of the integral of x squared plus y squared plus z ds, where c is part of the helix parameterized by r of t of cosine 2t, sine 2t, comma 2t, where t is bounded between pi and 0. Notice that this is a function curve that's same as the previous example. The only difference is the curve has been reparametrized so that it runs twice as fast. So what do you think will happen with this new parameterization? Well, let's go ahead and work it out and have an answer to compare. So again, I always like to write our formula. Our formula for such problem, we have our integral from b to a of f of r of t times r prime of t dt. Okay, so let's go ahead and begin by finding this f of r of t. So that we have, we have x squared plus y squared plus z, and we have cosine 2t for x, sine 2t for y, and 2t for z. So that I have cosine of 2t squared plus sine of 2t squared plus z, which is just 2t. Now we have cosine and sine squared. So we notice that that's going to give us a 1. So I have 1 plus 2t. That's that first part. Let's go ahead and now find that magnitude. Let's begin with the inside. Let's find r prime of t. So let's take our derivative of r. So we have to use chain rule. The derivative of cosine is negative sine. And our derivative of the inside is just 2. And then the derivative of sine is cosine. So I have cosine 2t. The derivative of 2t is 2. And the derivative of 2t is just 2. All right, let's go ahead and take the square root and square. So I have negative sine of 2t squared. There's a 2 in the front. And 2 cosine of 2t squared plus 2 squared. All right, so I'm left with 2 squared is 4. sine squared 2t plus 4 sine cosine squared 2t plus 4. We can factor out a 4, and then we're left with sine squared plus cosine, which is 1. And now we have 4 plus 4, which gives us the square root of 8, and we can simplify to be 2 square root of 2. So now we're left to integrate. Our bounds are from pi to 0, and we have f of rt, which is 1 plus 2t, and we're left with 2 square root of 2, which is a constant. We can move that forward if we like. And I'll let you integrate, and your answer is the same as the previous example. 2 square root of 2 pi plus pi squared. So note that changing the parameterization did not. It did not change the value of the line integral. All right, next example. The wire has a shape that can be modeled with parameterization of r of t equals cosine t comma sine t. And I'm going to change that one to be two over 3t to the 3 halves. And I'm changing that because this example is from the textbook and the work does not match this parameterization. So I'm changing the parameterization so that our work is not complex. Otherwise, it would not be as pretty. Now, our question is asking us to find the length of the wire. Now, remember, to find your arc length, we're integrating for 1. All right, so for us to translate it over into this type of problem, we have the integral for 1. This would be our integral. We're working from 4 pi to 0 of the magnitude of r prime of t. Okay, we're given a parameterization of r. Let's go ahead and find the derivative. So the derivative of cosine is negative sine. The derivative of sine is cosine. And that derivative there, well, we just simply use power rule, bring it forward, subtract by 1. We're left with just square root of t. Okay, let's go ahead and find that magnitude. So that we have negative sine of t squared plus cosine of t squared plus square root of t squared. That way the square is gone, and that's why I wanted to use this value for t. All right, we have sine squared plus cosine squared. We have 1 plus t. I think I should have made that long. 1 plus t. All right, let's go ahead and integrate. So now we're going to integrate from 4 pi to 0, and we have the square root of 1 plus t dt. All right, you can integrate this one. Let me help you with that u sub. So after you integrate, you're left with 1 plus t raised to the 3 over 2. You plug in 4 pi and then 0. Your answer should be 2 over 3, 1 plus 4 pi of 3 over 2 minus 1. All right, next we have vector line integrals. So I copied this chunk straight from the text because it's important and it was I don't think it was worth the effort of retyping it if I can just snip it. All right. The second type of integral are vector line integrals, which we integrate along the curve through the vector field. For example, let f of x comma y comma z be p of x comma y z I plus q of x comma y z j plus r of x comma y comma z k. Be a continuous vector field in R3 that represents the force of a particle, and let's see it be a smooth curve R3 contained in the domain of F. How would you compute the work done by F in moving a particle along C? To answer this question, first note the particle could travel in two directions along a curve, a forward direction and backward direction. The work done by a vector field depends on the direction in which the particle is moving. Therefore, we must specify a direction along a curve C. Such specified direction is called orientation of a curve. The specified direction is a positive direction along C. The opposite direction is a negative direction. So if you get a negative or a positive when you're integrating, it's simply telling you the direction from C. All right, and there you have your types of curves. Definition of a vector line integral. As with scalar integrals, it is easier to compute a vector line integral if we express it in terms of parametrization. Function r in variable t. So to translate the integral of f dot product t ds in terms of t, note the tangent vector t along C is given by r prime of t divided by the magnitude of r prime of t. So therefore, f dot product t is simply, so this is what you want to keep note, f of rt dot product r prime of t. And that's kind of our definition so that we can apply that line integral. All right, let's go ahead and do an example. Find the line integral of f dot product r, where C is a semicircle parameterized by r of t equals cosine t comma sine t, where t is bounded between pi and 0, and f is negative y comma x. Okay, so from our definition above, we said that is simply our change of variables and our derivative of our parameterization. All right, so let's go ahead and do our change of variables. So we have f of r of t. So for f, we're given negative y comma x. All right, let's go ahead and change these values. So I have negative, and for my parameterization, for y, I have sine t. So I have negative sine of t, and x is just cosine of t. So we have done that first part. Okay, now let's find that derivative of r prime of t. All right, so the derivative of cosine is negative sine of t. The derivative of sine is cosine of t. Let's use those two pieces to find our integral. So by our definition above, we have that the integral is f dot dr. And we saw that that's just our bound. In this case, it's from pi to 0. And our f is that negative sine t cosine t. And our r prime, which is that dr, is negative sine t cosine t, this one here. So this was that first one, that was that second one. I'm just noticing that in this case it ended up being the same values. Okay, let's go ahead and perform the dot product. So we multiply it first. So negative sine times negative sine is sine squared plus our second cosine squared t. I said plus, I wrote minus. So we see that we're left with, again, the Pythagorean rule. So we're left with just one, the Pythagorean identity, I mean. So our answer would just be pi. Application of line integrals. Scalar line integrals have many applications. They can be used to calculate the length of mass of wire, the surface area of a sheet on a given height, or the electric potential of a charged wire given a line charge density. Vector line integrals are extremely useful in physics. They can be used to calculate the work done on a particle as it moves through a force field or flow rate of a fluid across a curve. Here we calculate the mass using a wire using a scalar line integral, and the work done by a force using a vector line integral. All right, let's do an example. Calculate the mass of a spring in the shape of a curve parametrized by, so this would be our r of t, comma 2 cosine t, 2 sine t, where t is between pi over 2 and 0, with a density function given as rho of x comma y comma z of e to the x plus y z. And here we have a cute image of what's going on. All right, let's go ahead and translate this. So to find this integral, we have it defined by our theorem. It's f of r t, which is rewriting our f and then taking the magnitude of our derivative. That's what we have. So let's go ahead and try to get this. Let's split up these pieces. So we first have to find that change of variables. So I have f of r of t. Let's go ahead and do that. So we have e to the x plus y z. For x, we have t. For y, we have 2 cosine t. And for z, we have 2 sine t. Let's make that change. So I have e raised to the t plus 2 cosine t times, well, let's not use dots, not confuse it with a different operation, 2 sine t. And we can multiply those 2's together so that we have e to the t plus 4 cosine t sine t. All right, that's important. Next, I'm left to find r prime. So I have my r. Let's find that derivative. The derivative of t is just 1. Derivative of cosine is negative sine. So I have a negative 2 sine t. The derivative of sine is cosine, so I have 2 cosine t. All right, let's go ahead and add them and square them. One squared plus negative 2 sine t squared plus 2 cosine t squared. And we know what's going to happen with those sines and cosine squares. So I have 1 plus 4 sine squared t plus 4 cosine squared t. Let's factor out a 4. So that we're left with 1 plus 4, since that was just 1. So we're left with the square root of 5. All right, now based on what we have defined, now we can set up our integral. We have it from pi over 2 to 0, and we go ahead and find that value f of rt, which is e to the t plus 4 cosine t sine t times that square root of 5 we just found. And we can move that square root of 5 forward since it's just a constant. and then integrate from there. All right, let me help you with that integration. Once we integrate, we're left with e to the t plus 2 sine squared t from pi over 2 to 0. And your final answer should be square root of 5 times e to pi over 2 plus 1. All right, so what did we find? We were asked to find the density, or calculate the mass. So our answer is the mass of our value. All right, last piece for this section. It's a very lengthy section. Flux and circulation. Flux is used in application to calculate the fluid flow across a curve, and the concept of circulation is important for characterizing the conservative gradient fields in terms of line integrals. Both of these concepts are used heavily throughout the rest of this chapter. All right, so flux is defined as F of nt divided by the magnitude of nt. So we have an image of a flux here, and the figure reads the flux of vector field F across the curve C is computed by the integral similar to a vector line integral. Theorem 6.6, calculating flux integrals across a curve. Let F be a vector field and let C be a smooth curve with parametrization of R of t equals x of t comma y of t, where t is between a and b. N of t is a derivative of y prime t comma x negative x prime t. So keep that in mind. So our flux can be done by changing the variables and then finding that n of t, which is defined by this. Make sure you see this. All right, let's go ahead and do this last example. Oh no, we have one more. All right, let's go ahead and calculate the flux of F, where F is defined by 2x comma y across the unit circle or oriented counterclockwise. All right, so by theorem above, we said that it can be found by the integral of C by F of R of t dot product with n of t. Let's go ahead and find all those pieces. So f of r of t. So we have our function f. Now we need that r of t, we need that parametrization. So our parametrization is cosine t, sine t, since it's just a unit circle. And therefore, we have 2 times x, x is cosine of t, comma 2 sine of t, since it was 2y. And there we have it. So we have 2 cosine t, 2 sine t. All right, now we need to find n of t, which is our derivative, but it's kind of tricky. We want our y component, our derivative of our y component, and then the negative derivative of our x component. All right, so what do we get? Now, that's our x and that's our y. So the derivative of y, which is sine, is cosine t. And the negative, the derivative of cosine is negative sine. So our answer would be cosine t comma positive sine t. All right, and those are the two pieces I need to be able to integrate. Now, because it's along the unit circle, so the unit circle, just that phrase told us so much. It helped us find our parametrization And you know unit circle has a range of 0 to pi, so that's going to help us with our integral. So now we integrate from 2 pi to 0, and we're going to use 2 cosine t, comma sine t, 2 sine t, and then perform the dot product with cosine of t sine t. All right, if we perform the dot product, we get 2 times cosine and cosine, we get 2 cosine squared t plus 2 sine squared t. And cosine plus sine squared gives us 1. So if I factor a 2, I'm left with just 1. So I get 2. So we're integrating for 2 from 2 pi to 0, and we just get 4 pi. All right, last bit. Now we can now that we have defined flux, we can turn our attention to circulation. The line integral of vector field f along an oriented closed curve is called a circulation of f along c. The circulation line integrals have their own notation. So if you see a circle along the integration, that's just circulation along our f. The circle on the integral symbol denotes c is circular and it has no endpoints. All right, next example. Calculate the work done on a particle that transverses circle C on radius 2 at the origin, oriented clockwise by the field of f of x comma y equals -2 comma y. Assume the particle starts its movement at 1 comma 0. All right, so to begin, this circle of radius 2 center at the origin, it tells us a lot. So because it has a radius 2, or let me take a step back. Because it's along the origin, I know I have cosine comma sine. But because it has a radius of 2 and not of 1, we'll have a 2 in front. So that we have our parametrization. All right, so according to our definition, to find this work on our f, we have f dot t, right? So let's go ahead and perform this. So actually, better yet, let me use that other writing. So we're going to integrate by finding the change of variables of f along t. And then we're going to go ahead and find rt, which is our derivative of r. So r prime of t. All right, let's first begin with that change of variables. All right, r is here, r of t, let's take the derivative. Derivative of cosine is sine, so I have -2 sine t. Derivative of sine is cosine, so I have 2 cosine t. Okay, great, we got that done. All right. Oh, I did that wrong. We're supposed to change variables. I took derivatives. All right, so our f is -2 comma y. So I have a constant that's not going to change. And my y, well, my y is 2 sine t. 2 sine t. There we go. All right, let's go ahead and find t. Let's find that r prime. That's what I was doing that first time. Sorry about that. All right, so our derivative or our parametrization is -sine t 2 cosine t. Okay, let's perform the dot product. So that we have 2 pi to 0 of -2 comma 2 sine t dot product -2 sine t 2 cosine t dt. All right, we perform the dot product. 2 times -2 sine t, we get 4 sine t plus 2 sine t times cosine t, we get 4 sine t cosine t dt. All right, let me help you with that integration. If we integrate, we're left with -4 cosine t plus 4 sine squared t along 2 pi and 0, and your answer is 0. This means the force field does 0 work on the particle. All right, that's it for section 6.2, line integrals. Thanks.